According to ancient Chinese mythology, the goddess Chang'e and her husband were separated across the vastness of the Milky Way. To reunite them, a massive flock of magpies flew into the void, using their wings to form a bridge known as the Qiao. But the physical journey to the moon required the actual blast of rocket exhaust. In the early 2000s, China faced a steep reality. They had never sent a spacecraft beyond Earth orbit, and they lacked the deep space infrastructure to even track one. Building a deep space program from scratch left zero room for guesswork. The engineers needed an exact, highly disciplined roadmap to get off the ground. The China National Space Administration locked in a strict three-phase framework for their new Chang'e program. Phase 1, orbit the moon. Phase 2, land on the surface. Phase 3, collect a sample and return it to Earth. By forcing a massive astronomical ambition into 3 sequential, measurable steps, the program turned a centuries-old folktale into a highly executable engineering master plan. Phase 1 kicked off in 2007 with the launch of the Chang'e 1 probe. Its primary job was to survey the terrain and capture the nation's very first global, 3-dimensional map of the lunar surface. This grayscale image is the global orthographic map generated by the Chang'e 1 probe. Reconstructing the entire lunar sphere proved that the agency could effectively manage deep space telemetry and process complex planetary cartography. 3 years later, Chang'e 2 pushed that capability further. Engineers commanded the probe to drop to a perilous 15-kilometer orbit, skimming extremely close to the surface, to photograph specific landing zones at a razor-sharp 1.5-meter resolution. That precise scouting data fed directly into Phase 2. In 2013, using the detailed imaging from the orbiters, engineers safely put the Chang'e 3 lander down on the near side of the moon. With the lander intact on alien soil, Phase 1 was complete. The navigational data gathering worked exactly as designed, establishing the telemetry and landing coordinates required for physical surface operations. The next step of Phase 2 involved a much harder target, landing Chang'e 4 on the moon's completely inaccessible far side. The moon is tidally locked to Earth, meaning its rotational period matches its orbit, so it always shows us the exact same face. Because of this, the solid mass of the moon permanently blocks radio waves from Earth, creating a massive communications blackout zone on the far side. You cannot land a spacecraft if you cannot talk to it. So months before the lander ever launched, engineers placed a relay satellite called Qiao, named after that mythical magpie bridge, into a halo orbit 65,000 kilometers past the moon. Out at this gravitationally stable spot called the L2 Lagrange point, the Qiao satellite has a constant line of sight to both the Earth and the lunar far side, acting as a mirror, bouncing data seamlessly between the two. Through that constant radio link, Chang'e 4 safely touched down in 2019, deploying the U-22 rover to analyze materials originating deep within the lunar mantle. Executing a blind landing on the far side proved that the agency had constructed a deep space communications architecture robust enough to handle the most difficult robotic operations. That led straight into the final stage. Phase 3 required sending a lander to scoop up lunar soil and then launching a small ascent vehicle right back off the surface. Lifting off was only part of the problem. To get that sample back home, the ascent vehicle had to autonomously align and lock onto a return module, traveling thousands of miles per hour in lunar orbit, with 0 human pilots on board. In late 2020, Chang'e 5 executed that choreography flawlessly, parachuting a capsule containing over 1,700 grams of near-side lunar rock into a snowy field in Inner Mongolia. This 20-year progression culminated in the summer of 2024 with Chang'e 6. The mission required combining every single capability developed so far to attempt a sample return from the Apollo basin, located entirely on the far side. Because a far-side operation required huge amounts of data for tasks like controlling the Jinshan mini rover, they deployed a heavier, upgraded relay satellite, Kakao 2, into a specialized, highly elliptical frozen orbit to handle the bandwidth. On June 25th, Chang'e 6 delivered those far-side samples to Earth. Lifting material from the dark side of the moon and flying it home validated a 20-year bet on strict, incremental engineering. In 20 years, the CNSA moved from basic orbital mapping to precise far-side planetary choreography. But the real output of the Chang'e program is the permanent deep space infrastructure that was built along the way: the high-resolution maps, the heavy-lift rockets, and the relay satellites. That exact infrastructure is now being repurposed to support an even larger objective: the International Lunar Research Station, a planned surface base targeted for the late 2020s. The mythological Kuekiao was a temporary bridge built for just one day. The engineering master plan forged a permanent one, securing the lines of communication needed for a sustained presence at the International Lunar Research Station.